One last section here for Lesson 7 in Unit 5. We're looking at an even better fit. And for this, I'm also going to be using a little applet that they have preloaded on the Illustrative Math website. So this might be linked in your Google Classroom, or you could also find it just by looking at the student materials that we have. So a heads up that we're going to go use that info. It's already got this data preloaded, and the equations are entered and ready for us to work with. This one is telling us about this earlier lesson we looked at where we had left a bottle of soda outside for a certain number of hours. It seemed like the data points started at about 68 or 69 degrees-ish and tapered down to what looked like an asymptote right about here at about 45. So we have a very clear exponential decay going on, or this idea that nice exponential graph. And in fact, they give us now the equation for that exponential graph here. So it starts us with an exponential. That starting exponential graph is in your workbook, drawn on the right here. And it has the shape that fits, but we obviously need to move it up because it's far too low to actually be fitting the data. So we want to find a translation that would fit this data, write an equation for it that would model that data, and then what does that tell us about the temperature outside is what we're really looking for. So it makes sense to me to go to this applet and see what we're looking at. So I went to the Illustrative Math website, and we are in Unit 5. I went to Lesson 7. And so it looks an awful lot like this. When you scroll down, you'll see the points that we've already looked at, vertex form and all that good stuff. Here's that data preloaded. And so I can see all that data, and if I move this enough, I should see that graph where it's got the A, B to the H. And so I'm going to use what they have in the workbook and start putting some information in, because they're starting us with this graph of 33 times 0.6 raised up to the H power. Now I want to move this graph so it better fits all of this data, and I can do it by using a slider to change A and B, but we already adjusted A and B. So some of this data looks pretty decent, you know, not too different. I know that we definitely want to slide it up. So I'm going to just kind of start adding some ideas. You could also make it a slider here, that if we were to add something like A, but then you'd have to also change these values for what A begins as. So instead, I'm just going to try adding something. My values were way down low, so let's just try adding something like 30 to begin with. And I see that I'm getting closer. That's kind of nice. Oh, I thought there was a second data point out there, but I guess not. So I'm getting a little closer. I think I still need to lift it up higher. Oh, and that's looking pretty good. I put in 45, and that graph is lining up pretty well. We're just going to kind of play around with it. It's almost like one of those marble slider values. And we've added something to it at the end here to see if that helps. I remember before that there were two students who were arguing about a better fit for this, and I think one of them was starting to move this graph left and right as well. So in addition to moving it up like I have, I think it looks like I might also want to move it just a smidge to the left, because it's missing all of these data points here that I want to catch. So to move it to the left, I need to add something to my H. So I have my cursor up with the H. I keep on trying this. If we did something like H, I'm going to try +2 and just see what that does. It looks like that's moved it a little bit too much. I didn't want to move it quite that much. So let me just try a 1. Oh man, that's looking pretty good. Just try if I inch this up a smidge more. Man, that's looking darn close. Look at that, at how good we have that. That's looking pretty awesome. So I'd say that adding 1 to our H value, again, that moved us to the left 1 unit, and adding 46 seems to get us really close to all this data. Adding 45 is pretty close. Adding 47 is pretty close. really anything in there seems to be making sense to me. So going back to our workbook, some information that I would be writing down here. I'd be saying to describe a translation that better fits the data. To describe it in words, we should raise it up about 46 units. And to the left, 1. And so to write that equation of function g, modeling our data, g of h, thinking about the inputs that they're using here with the hours, was the same starting equation that we had for f of h, 33 times 0.6 raised to the h plus 1 in our exponent, and then adding 46 to it. Seems to be a pretty nice fit. This function tells me that my outside temperature, because this cold bottle of soda that we put outside seems to be cooling down until it reaches about a consistent outdoor temperature, tells me that that outdoor temperature is somewhere around about 46 degrees. It's approximately 46 degrees Fahrenheit. Because it's hitting that asymptote, it's going to match the outside temperature, but not get any colder or warmer than that. So to kind of pull a little bit of summary, we've got some summary pages for your lesson 7 in the workbook, and it's nice sometimes to look at those and just kind of see what they say. We can think about how we could describe a sequence of translations and reflections of the graph just based on what we're seeing is the changes that's going on. So if we started with f of x equals e, that would be our base for this equation to the x power. And the changes that I would see from that basic, what we call a parent function, to this new one, there's a negative in front of x, and then there's this plus 5 going on. So that negative x is going to reflect all of our x's. So that would be reflecting over our y-axis. And then it would move it up 5 units. Just being able to explore these and see what kind of differences they're looking like is really, really helpful. Starting with a parent function like x squared, we can see that this would be back to that idea of vertex form. This would, negative out front would flip it upside down because it's not reflecting over the, not changing the x left and right anymore. This one's changing vertical up and down. So this is going to reflect over the x-axis this time. It's going to go upside down. And the 3, that minus 3, would move us to the right 3 units. In comparison, this last one down here, this one has the negative in front of the x. That means it's flipping it on our x, all of our x's from positives to negatives. So it's going to reflect over the y-axis. It's going to move it now to the left 2 units. And then it's going to bring this thing down 6 units. You could do each of those one step at a time in Desmos and just see what it does, starting with each parent function and then just adding one element at a time to see what it does to this graph. But it's nice to be able to look at these expressions and interpret what's going on. If you have the cool down, it's asking you to write an equation for the function g whose graph is the graph of this guy, f of t, except this time translated 5 units to the right. So wherever I see that equation or that variable happening, I need to do a t minus 5 to move it to the right 5 units. And then up 50 units. So I'm just putting what was outside that exponent. Everything else is going to stay the same, but we're just putting in that to the right 5 here with the exponent. Wherever that variable is, moving it left and right is going to go wherever that variable is. Here it's in the exponent. And then we have to move it up 50 units, so we're going to tack on a plus 50 at the end. You guys are pros now at how to rewrite expressions and equations to match translations.